center of mass of a half circle. So I put semicircle. I think that's the same thing. And centroid and center mass. Center of mass is the weighted average of the masses in the object. And the centroid is the center of the area. But if the density is constant and the gravitational field's constant, those two things are the same. So here's my half circle. I want to find the center mass. I mean, if I did the center of mass for a circle, it'd be right there in the center. I mean, I think that's probably obvious. You could do that integral. It'd still be fun, but it's not the same thing. So let's say that we have a semicircle of mass m, total mass m, radius r, going from negative r to r. And so the x center mass is 1 over the mass times the integral of x times each mass that you integrate. So if I break this up into little pieces, here's my little dm. And in Cartesian coordinates, dm would be sigma dx dy, where sigma is just the area mass density. It's the mass per area. And it's not a super important thing, and I'll probably drop that out quite a few times, but that's what that is. Now, if I wanted to find the x center mass using that little piece, I could find its x value, I could find its y value, which I don't need, but I do need dx and dy. That's pretty easy to find. But what's not easy is to add these up with limits of integration, because it's a circle, so I'm not going from negative r to r. My limits of integration depend on my y value, and so it's not really nice. We could use polar coordinates, and I will, but we're also going to use another trick. So let's add up objects like this. I'm going to break this into vertical rectangles of width dx. And I can use this as my dm. And so you notice right here, this has a height of y. So in this case, my mass dm is going to be equal to sigma times my width of my rectangle, which is dx, times the height of my rectangle, which is just y. And the center of that is x, right? So this piece, as I add up going this way from negative r to r, the x value of that piece is the center mass of that piece is x. So I can just integrate x over the whole thing, and that's what I'm going to do. And the x center mass is actually boring, but it's a good warm-up exercise. So let's just write down this. X center of mass is 1 over the mass. I always forget that. Now, I don't need to do a double integral because I can just add these up from x equals negative r to positive r, and I'll get the whole thing, right? Because I'm slicing them vertically. So I'm going to say x equals negative r to r x dm, which is 1 over the mass, integral from negative r to r x, and then my dm is going to be equal to sigma y dx. Now, I can't do that integral because I have an integration variable dx, but I have the variable y right here. But it's fine because I can say, what's the equation of that circle? I can say that's x squared plus y squared is equal to r squared. That has to be true on that circle, right? So the height of that, the y value, depends on the x value based on this equation. So I can say y is the square root of r squared minus x squared and put that in right there. So now I get x center mass is 1 over the mass times the integral from x equals negative r to r x sigma, and then I get the square root of r squared minus x squared dx. Now you can do this integral. It's not impossible to do. You can look it up in a table. You can do a bunch of things, but the answer is 0. Why is the answer 0? Well, because I'm integrating over from negative r to r and a symmetric limits, and I have an odd function. X is an odd function, but this is an even function. So an odd function times an even function is odd, and the integral over an odd function over a symmetric interval is 0. So it'd be like integrating this, right? Y equals x. This positive value and this negative value are equal and opposite, so the total integral is 0. I know that's a little bit of a letdown, but I want to do the other integral, and so that's more important. Okay, so now let's do the y center of mass. So let me just redraw my circle here. I'm tracing it so I can see it on my paper. So here's my dx. And I'm going to say the y center of mass is 1 over the mass times the integral from x equals negative r to x equals r of y dm. And I still have the same dm, so this is 1 over the mass, integral from negative r to r, y, and then remember the height of that is, actually this is not y, this is y over 2, right? Because right here is the location of my center of mass. As I move along here, the center of mass of each piece is not y, it's y over 2, right? So it's y over 2. That's my location of the center mass. And then the dm, so this is y, I'll put the 1/2 right there. The dm is sigma y dx. That's the whole thing. I'm going to pull out the sigma and the 1/2. So I get y center of mass equals 1 sigma over 2m negative r to r. And then I have a y squared dx. But y squared, remember, y squared is r squared minus x squared. So I get r squared minus x squared dx. And that's not too terrible of an integral to do. I am going to make one quick amendment, because now I have an even function. I'm integrating from here to there. I could just as easily integrate from here to there and double it. And you can see that from the picture, but you can also see that because this is an even function. So I'm going to write this as y center. And it honestly, it just makes me feel better, because when I do negative r as one of the limits, I always make a sign error, and I don't like to do that. So I'm going to say this is equal to 2 sigma over 2m from 0 to r squared minus x squared dx. And that's not too bad of an integral to do. So the 2's cancel right there. So I get sigma over m. And then the integral of r squared dx is just going to be r squared x. R squared x. And then the integral of x squared is going to be minus x cubed over 3. And then I need to evaluate that from 0 to r. So my I had the m. Y center of mass. I always forget that m. That's why I just said, wait, I didn't have my m. So it's going to be sigma over m. And then this is going to be r squared times r minus 0, which is 0, and minus r cubed. So I get r cubed minus r cubed over 3. So this is like 3 over 3. So I get 2 r cubed over 3. 2 sigma r cubed over 3m. Now let's put in our value for m. So if this is half of a circle, then the mass is just going to be sigma times pi r squared, all of that over 2. It's half of the total mass of a circle. So if I put that in, I get 2 sigma r cubed over 3. Now I'm going to put in this sigma pi r squared over 2. So I'll put the 2 up here. So the sigma cancels, some of those cancel, and I get 4r over 3 pi. And that's my y center of mass. That was fun. Okay, let's do it again. Okay, I'm going to draw my picture right here. So it's a circle, so it might be better to use polar coordinates, right? So if I can represent the piece as a polar coordinates piece. So in polar coordinates, if you just draw, let me draw it a little bit bigger. So there's my area element in polar coordinates. This is r. This is going to be dr, right? It's because I increase r by a little bit. If I increase theta by a little bit, it's this distance right here, which is r d theta. So that means my area dA is going to be r dr d theta. And my mass dm is going to be sigma r dr d theta. I'm not going to do the x coordinate. We already showed that was 0 and it's boring. But I do want to do the y center mass. So let's write down the y center mass. The y center mass is going to be equal to 1 over the equals 1 over the mass. Now I have to do a double integral over from theta equals 0 to pi. That's that way. And from r equals 0 to r. So I'm going to integrate this way and this way. And then I have y dm. Now, I have my dm, but I also need to get my y, right? So if this is r and this is theta, then that's y. So y is r sine theta. So if I put that in, I get y center mass is 1 over the mass. R equals 0 to r. Theta equals 0 to pi. And then I get r sine theta, r dr d theta. And of course, we should write that better. Y center mass, sigma. Sigma over m, 0 to r, 0 to pi. I'm going to put all the r stuff. I have r times r, so it's r squared dr. And then I have sine theta d theta. And so since this theta doesn't depend on r, I can just do the theta integral first. So I get sigma over m, 0 to r, r squared dr. And then the integral of sine theta is going to be negative cosine theta from 0 to pi. And so if I put this in, I get cosine of pi is negative 1. Cosine of 0 is 1. So I get negative 1 minus negative parentheses. I'm going to write that out. This is going to be negative 1. No. It's going to be negative 1 minus 1. So it's going to be 2. That one's tough. This is 2. I made this mistake before. Okay. So that's 2. So we can bring that out front. And now we have the y. Am I running out? No. Y center mass is going to be 2 sigma over m from 0 to r. And I get r squared dr is going to be r cubed over 3. Oops. I did the integral already. From 0 to r. Yep. And so I get 2 r cubed over 3 sigma over 3m, which is the same thing I had before, because now if I put in my mass, I get 2 sigma r cubed over 3 pi r squared over 2, and that's going to be equal to 4r over 3 pi y center mass. It's the same thing. Fun, right? I said 3 ways, and there's actually another way that we could do this. There's many ways you could do this, and that's what makes it fun, right? We're doing it for fun. Okay. Now we're going to do it the way that I like to do it. So imagine that I have I'm going to draw a little bit bigger, my half circle. And instead of writing x center of mass is 1 over the mass double integral x dm, I'm going to write x center mass as 1 over the mass times the sum over I xi mi. So suppose that I broke this into a bunch of pieces. And they don't have to be squares. I'm just drawing them as squares. And so each one of these pieces has a mass where this is, let's say, in pieces. In pieces. I'm going to spell in things. I'm going to spell pieces. In things. You know, that's a trick. If you think you're going to misspell something, just use a different word. That's the nice thing. So in that case, each one of these, mi, would be the total mass over the number of pieces I break it into. And now each one has a coordinate, right? x1, x2, x3, x4, and so forth. So I can just literally take each mass, which are all the same, take each x value, add them all up, and then divide by the total mass, and that will give me my thing. And so how do I make all these points? How do I break this into n points? And the answer is random numbers. And I know this is kind of just silly. You definitely don't have to do it this way. We already did it, so we didn't do it this way. But there are some problems that using random numbers makes it a lot easier. And so this is just a chance to practice that. So I'm going to break this into n pieces in random numbers in Python, and I'm going to give you the code. Now, here's the trick. The Python I'm using really only has one random function. It's called random. And this gives you a number between 1 and 0. Random parentheses, 1 and 0. That just gives you a random number. And if I want to go from negative r to r, I actually want to generate x and y values for all these, right? So I can say my x values I want to be from negative r to r. So x, I'm going to say, is equal to x temp. It's going to be r times 2 times random minus 1. Because 2 times random is now a number between 2 and 0. When I subtract 1, I'll get a number between negative 1 and 1, multiplied by r, and there you go. My y is going to be equal just to r random. R times random. And that will give me a number between 0 and r, right? I don't really care about the bottom. This is going to be my origin right there. Now, I do need to do something here. If I'm going to do this, I'm going to add these up as numbers, I need some numbers. So I'm going to need r. Let's say r equals 1. That seems to make sense. Mass is 1. Sigma is 1. And that's what we're going to do. Okay, jumping over to Python. Get ready for some code. It's going to be fun. Okay, so here's my Python code. It's blank. I'm using WebVPython. And let's just jump into it. So the first thing I said was r equals 1. I'll call that sigma. Let's just call that s. I don't want to write out sigma. Sigma is 1. M is equal to 1. N is equal to 100. I'm going to make 100 points because I just lied. My random numbers were wrong, right? I'm going to do what I said, and I'm going to show you it doesn't work. So let's do this. N is my number of points, and n equals 0 is my counter. So I'm going to say while n is less than n equals n plus 1, and then print. I'm just showing you that works. And there you go. There's my numbers. Okay, awesome. Now I want to actually make let's make a random vector between negative r and 0 and r. So I'm going to say rt equals r times, and r is 1, then you need to put it there, vector. My x coordinate is going to be 2 times random minus 1, and that's right there. And then my y coordinate is just going to be random. I've already multiplied by r, random, and then my z coordinate is 0. So this is going to make a random vector point. Now I want to draw a sphere there, so let's make a just so we can see what it looks like. We could plot this, but let's just make it as a sphere. I should plot that. Oh, let's make it as a sphere. Okay, so I'm going to say sphere position is RT. Radius of the sphere that I'm drawing in there is going to be equal to R over 20. I think that's fine. Let's just see what it looks like. That's 100 random points. There you go. And it doesn't look like half a circle, does it? Because it's not. Let's make that a little bit smaller. R divided by 40. And let's make it 300 points. There. Not a half circle. So these points up here and these points over there, I don't want to use, right? I want to throw those away. So I'm going to put in here, I'm going to generate that random vector, and then I'm going to say if the magnitude of RT is less than R, then I want to keep that point. So if it fits in the circle, then the magnitude of the vector is going to be less than or equal to R. I can say less than or equal to, it doesn't really matter. And so only in that case do I want to make the sphere, and only in that case do I want to add 1 to my counter. So if I do that, now I get this. There, now I have 300 points in a half circle. All I need to do is to calculate the center mass. That's all I need to do. And this is in 3D, just in case you really want to look. It is kind of fun to play with. I'm not going to display them because it slows it down a lot. So I'm just going to comment this out. Now let's do this. Mi is going to be equal to m divided by n. Each one has a mass of just part of that. You don't really have to do this, but I'm going to do it anyway. And now I'm going to say x center mass equals 0, y center mass equals 0. So since it's a sum, I need to start somewhere. I'm going to start with x center mass is 0, and every time I calculate a point, I'm going to add it to that, add it to that, add it to that. Okay. So I have my vector, and it's in the sphere, so I'm going to add these to those things. So I'm going to say x center mass equals x center mass plus rt dot x, that's that x coordinate I just created, times mi. Y center mass equals y center mass plus rt dot y times mi. And that's it. And let's print those. Print, you can't see that. Print x center mass equals xcm, and don't worry about the units. And then let's print y center mass equals ycm. And then let's print the theoretical center of mass. So print y theory. And we said that was equal to, what was it? 4r over 3 pi. So 4 times r divided by 3 times pi. Okay, let's run that. And this is just 300 points. Okay, so right here, my x center mass, it's not 0. We said it should be 0. It's not 0. That's okay, right? Because it's just random. It's close to 0. And then my y center mass is 0.4. The theoretical is 0.42. So that's pretty close with just 300 points. Now, if I run it again, I'm going to get a different answer because it's random. Look how close it got that time. But wait, I could change this to 3,000 points. It doesn't really change the program too much, and it works a lot better. Look how, and then run it again to see. Oh, that's pretty close. I could change that to 10,000. I don't think it will break. I think it'll be okay. Okay. That's pretty good. So that's called a Monte Carlo calculation, using random numbers to calculate the thing. And it's just fun. It's just fun, right? And the code's not even that bad, right? That's not bad code. So let me save that. Monte Carlo Centroid. That's fine. And I'll give you the link to that code down below. And there you go.